Hello. Now we are going to continue our work in algebra with binomial expansions. And binomial expansion, bi means two, nomial means term, expansion is multiplying out brackets. So binomial expansion is just where we're multiplying out brackets that have two terms in them. And in this case, I've written them as a plus b, but they can be more complicated terms. But if there's two terms in a bracket and we are multiplying them out, we are squaring them or cubing them or to the power of 4ing them, that's what we're doing here with binomial expansions. Now, I've already written this a little bit out as an introduction. So if I have a plus b, two terms, binomial, to the power of 0, and I expanded that bracket, anything to the power of 0 is 1, so I just end up with 1. If I have a plus b to the power of 1, I end up with 1a plus 1b. If I have a plus b squared, a very common thing that we've multiplied out lots of times, we end up with 1a squared plus 2ab plus 1b squared. Very familiar with that one. Less familiar with these, but you can do them out in exactly the same way. A plus b cubed would be 1a cubed plus 3a squared b to the power of 1 plus 3a to the power of 1b squared plus b cubed, and a plus b to the power of 4 would be 1a to the power of 4 plus 4a cubed b to the power of 1 plus 6a squared b squared plus 4a to the power of 1 b to the power of 3 plus 1 b to the power of 4. Those are just facts. We can go the long route and multiply all of them out. We will find that those are the answers that we get for having different powers on our brackets of a plus b. But there's, as so often in maths, a pattern that we can spot going on here. If we look at the coefficients, we'll start off by talking about the coefficients. There's other patterns too. If we look at the coefficients of our terms that we get out from these different powers on our brackets a plus b, the first, when we have power of 0, we end up with a coefficient of 1, regardless of what's going on, or just 1 as our answer. Then a plus b to the power of 1, we end up with a coefficient of 1 and 1 for a and b. For our very familiar a plus b all squared, we have 1, 2, 1, 1, 2, 1. So 1a squared plus 2ab plus b squared, 1b squared. For our cube term, we can see that we end up with first coefficient is 1, 3, 3, and 1. And for the power of 4, we end up with 1, 4, 6, 4, 1 for our coefficients in terms of in front of our terms. So when we do that, we see that we end up with a pattern. If we draw out the coefficients, and Pascal was one of the first people to do this, he was a very important philosopher and mathematician. And when he wrote out the coefficients when he was getting the powers of different brackets a plus b, to different powers, he ended up getting this pattern here, where we ended up with 1 as our top term, and then 1, 1, and then 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. And if we think carefully about this triangle or pyramid, we can see how to generate the next line in this pyramid. Now, this might seem a little bit arbitrary. It has come up on the exam. That's why it is I'm going to focus on it a little bit here. But if I start off with 1, the way that I generate the next line is that I want to add the two terms above the term on the next line. So I imagine that there's zeros or nothing out here. So nothing plus 1 is 1. Nothing plus 1 is 1. 1 plus nothing is 1. 1 plus 1 is 2. 1 plus nothing is 1. Nothing plus 1 is 1. 1 plus 2 is 3. 2 plus 1 is 3. 1 plus nothing is 1. You can see how this is generating. So what would be the next line? We'll write it in blue. Well, I'd have nothing plus 1 is 1. 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5. 1 plus nothing is 1. So that would be the next line of our Pascal's triangle, which again is giving us the coefficients of the terms when we multiply out our different powers on our brackets. Keeping in mind that if we look at our number of terms, we end up with effectively n plus 1. If n is the power on our bracket, we end up with one more term than n. So if we have 0, we have one term. If we have power of 1, we end up with 2 terms. If we have power of 2, we end up with 3 terms. So we end up with the power plus 1 number of terms, and Pascal's triangle is giving us the coefficients of those terms. Again, this is a pattern that was spotted early on, well, not terribly early on in the history of maths, but early on in modern mathematics, and is something that has come up directly on the exam. So you must be able to form Pascal's triangle by adding up the terms above the last term in our sequence, in our pattern. So that's the first big pattern that we see when we're multiplying out powers on our bracket. The other one is what's happening with the powers on the terms. So if I look at the example of cubed, which is where it starts to become a little bit more obvious, I start out with the first term cubed, so the first term with the power that was on the bracket. And then if I look at what happens to the powers of a as we go to the right, a cubed, a squared, a to the power of 1, and if you like to imagine it, a to the power of 0, which would just make it 1, which means it doesn't show up. If I look at the powers on b, we can imagine that it starts as b to the power of 0, then b to the power of 1, b to the power of 2, b to the power of 3. So the first term's power starts out at the power on the bracket and decreases down to 0. The second term's power starts at 0 and increases up to the power on the bracket. And you can see that again on our final set here. We have a plus b to the power of 4. So we have a to the power of 4, a to the power of 3, a to the power of 2, a to the power of 1, a to the power of 0. So you can see that this is a pattern in our terms. And it turns out we can actually write that in a very specific fashion. We can combine what we know about Pascal's triangle and this pattern of powers increasing and decreasing for our first and second term in what's called the binomial theorem. So again, binomial just means 2 terms. So this is multiplying out brackets with 2 terms in it with different powers. And it's what is written here, and it's on page 20 in your log tables, the algebra page. So log tables, page 20, is where we're going to get our binomial theorem. And it looks very arbitrary and funny, but one of the things that jumps out at us perhaps is this funny business with brackets. This kind of almost looks like a fraction, but it ain't. What it is called a combination, and we are going to deal with them in detail. We're going to deal with what a combination actually is when we come to the second part of probability, so advanced probability. For right now, all we need to know is how to put it into a calculator. So if I take something like 5C1, which is how you are going to say it in the long term, if I have 5C1, what does that mean in terms of what I'm going to do on my calculator? It means 5, and then I'm going to look for the capital C button on my calculator. On lots of your calculators, it's going to be the second function divide, but it won't be the same on all of your calculators. So second function and divide, you'll be able to see will have a button usually labeled as, your button will look like n, little n, C, or. That's what the button on your calculator will look like for most of you. And how we write that on is 5, and then second function C will give us something that looks like C, and then we type in 1 and equals, and that is going to give us 5. Just to touch on where this is going to go in the long run, this means if we have 5 items, how many ways can we choose one of them? But we don't really need to worry about its meaning right now. I'm mentioning it as a bit of an anchor for when you come back to it in probability. So if we have 5 items, how many ways can we choose one of them? And again, on the calculator, if we had 5 C2, we'd have 5. Second function C is going to give us 5C and then 2, hit equals, and you are going to get the number 10. For right now, all I'm concerned about is that you can put this into the calculator. We will spend time making sure that it is very understandable and reasonable when we get to doing the second chapter or the more advanced part of probability later on this year or next year. Now, to give you an example of implementing this, I'm going to take a plus b to the power of 4. So the longest one of these that I did out before. And I'm going to use this formula, the binomial theorem, in order to figure out what it is going to come out to if I multiplied out my brackets, if I expanded my brackets. So in my formula, I have x plus y to the power of n. So I want to state what my bits are from my formula. So I have x is going to be equal to a, y is going to be equal to b, and n is going to be equal to 4. And now I'm going to follow this here. The easiest one to read is, or it's certainly the easiest one to start, is the expanded form here, so the larger bit of writing. So that's going to be 4c0. We know what that's going to be. It's just going to be e4 second function c 0 multiplied by x to the power of n is going to be a to the power of 4 plus 4c1 a to the power of 4 minus 1, which is just going to be 3, on b to the power of 1 plus 4c2 a to the power of 4 minus 2 multiplied by b to the power of 2 plus 4c3 a to the power of 4 minus 3 b to the power of 3 plus 4c4 b to the power of 4. So I end up with, when I put this into the calculator, 4c0 is going to be e1 a to the power of 4 plus 4c1 is 4 a to the power of 3 b to the power of 1. 4c2 is 6 a to the power of 2 b to the power of 2 plus a to the power of 1 b to the power of 3 plus 4c4 is 1. Sorry, that should be 4. 4c3 is 4. 1b to the power of 4. So you can see that our binomial theorem, a bit along the bottom, has given us exactly the same answer as if we had multiplied this out the long way. And it turns out that they can ask you in the exam for a plus b to the power of 7 or 10 or something unpleasant like that. This formula makes that fairly quick and comfortable to do. Trying to do it out by multiplying out brackets over and over and over again becomes extremely difficult and almost guaranteed to make a big mistake that will dock us lots of marks. So this binomial theorem is very important for some parts of the course where we need to multiply out brackets with high powers on them.